Welcome to the Sleepy Scholar. It's lovely to have you here tonight, wherever you happen to be. Maybe you're tucked under a heavy blanket with just one lamp still glowing in the corner. Maybe you're on a train, or a couch, or lying flat in the dark with your eyes already halfway closed. However you've arrived, settle in. There's no hurry here. There's nothing you need to do, nothing you need to remember, nothing you need to hold on to. Tonight we're going to drift, slowly and gently, out into the quietest and strangest corners of the universe, and if you fall asleep somewhere along the way, that's not a failure. That's the whole idea. The stars will still be there when you wake. So will the ones that are barely stars at all. And before we go any further, where in the world are you listening from tonight? What time is it in your corner of the night? I always love wondering about that, all of us scattered across the planet, awake in the dark together for a little while. If you enjoy these slow journeys and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you already here, already part of this quiet ritual, thank you. Truly, now let me make my usual promise and my usual small joke. I'm going to try very hard not to make tonight so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely about the dark. A fair trade, I think. So, let's begin, shall we? I want you to picture our galaxy, the Milky Way. It's a vast thing, a great spiral wheel of stars, hundreds of billions of them, turning slowly in the black. When you look up on a clear night away from the city and you see that faint river of pale light spilling across the sky, that's us. That's the disk of our own galaxy seen edge-on from the inside. It's so full of stars that we can't even count them properly. We estimate, we guess. Hundreds of billions of suns, each one a furnace, each one blazing away across unimaginable distances. That is what a galaxy is supposed to look like. Crowded, luminous, loud with light. Now I want you to imagine something almost impossible. Imagine a galaxy that is just as wide as ours. Just as sprawling, tens of thousands of light years across, a great disk of the same enormous size. But when you go to count its stars, you find only 100th as many. Not 100 times fainter, 100 times fewer. Where the Milky Way holds hundreds of billions of stars, this one holds only about 1% of that. A whole galaxy the size of ours, and yet almost empty. Almost dark. So thinly populated with starlight that for the longest time nobody even knew it was there. That galaxy is real. It has a name. It's called Dragonfly 44, and astronomers found it in 2015. Two researchers in particular, a man named Pieter van Dokkum and his colleague Roberto were behind the discovery along with their team. Dragonfly 44 lives in a great swarm of galaxies called the Coma Cluster, which sits about 320 million light-years away from us. Let that distance settle over you for a moment. 320 million years is how long the light we're seeing has been travelling to reach us. It left that faint, ghostly galaxy long before there were any human eyes to catch it. Before there were people at all, and it has been crossing the dark this entire time, just to arrive here, tonight, in the quiet, while you drift towards sleep. And here is the thing that makes Dragonfly 44 so haunting. It isn't small. It isn't some little dwarf, some minor smudge of a thing. It's big. Genuinely, properly big, on the scale of our own grand Milky Way. And yet its stars are so few and so spread out that it barely shows up at all. It's like taking a small town's worth of streetlights and scattering them across an entire continent. Each light is still there, still burning. But stand back far enough, and the continent looks utterly dark. You'd never guess anyone was home. So how do you even find something like that? How do you find a galaxy that is almost invisible? To understand that, we need to talk about a strange and beautiful idea, and I'll go slowly, because it's the kind of idea that's easy to feel even when it's hard to grasp. Astronomers have a way of measuring how bright a patch of the sky is, not the total light of an object, but how concentrated that light is across the area it covers. They call it surface brightness. And it turns out that surface brightness, not total light, is what makes these galaxies vanish. Think of it this way. Imagine a single candle in a dark room. Held close, it's bright, easy to see. Now imagine taking that same amount of candlelight and smearing it out across an entire wall, a great wide surface. The total amount of light hasn't changed at all. But now it's so spread out, so diluted, that the wall just looks dim, faintly glowing maybe if you squint. That's what happens with a galaxy like Dragonfly 44. It has a real amount of starlight in it. But that light is spread across such an enormous area that any single patch of it is barely brighter than nothing. And here is the part that I find genuinely astonishing. The part I want you to carry with you into your dreams. These galaxies are so faint that they are dimmer than the night sky itself. I don't mean the night sky with its stars, I mean the sky between the stars, the seemingly empty black. Because here's a secret about that blackness. It isn't truly black. Even on the darkest, clearest night, far from any city, the air above your head is very, very faintly glowing. It's a phenomenon called airglow. High up in the atmosphere, atoms and molecules that were energized by sunlight during the day slowly release that energy back out as an incredibly dim light all through the night. Your eyes can't really see it, but sensitive instruments can. The empty sky is quietly luminous. And these ghostly galaxies? Their brightest, most crowded central regions are fainter than that. Fainter than the glow of the empty air. Astronomers put numbers on this, and the numbers are almost poetic in how they describe the near impossible. They measure surface brightness in units called magnitudes per square arcsecond, and the fainter the object, the higher that number climbs. Something around 24, 25, even 26 or 27 magnitudes per square arcsecond is astonishingly dim. Dragonfly 44 and its kin live down in that range. To find them, you are quite literally searching for something dimmer than the glowing air above your own head. You're hunting a shadow that is darker than the dark. For decades, this is exactly why we missed them. Our telescopes, for all their power, were tuned to catch bright things, sharp things, points of concentrated light. A galaxy that spreads its light so thin that it sinks below the glow of the sky just slipped right through. It was there the whole time, hanging in the black, and we looked straight past it. Thousands of them, as it turns out. But we'll come to that. Now I need to pause here and untangle two ideas that sound almost the same but are truly, importantly different. Because this is the kind of thing that even careful people get muddled, and getting it clear now will make everything that follows so much more satisfying. There are two different kinds of nearly invisible galaxy we're going to talk about tonight. And though people often blur them together, they are not the same thing at all. The first kind is called an ultra-diffuse galaxy. That's a bit of a mouthful, so let me just decode it plainly. Ultra-diffuse simply means very, very spread out, extremely diluted. An ultra-diffuse galaxy is a galaxy that genuinely has stars. real stars, actual burning suns. It's just that those stars are scattered so thinly across such a vast area that the whole thing is faint, almost to the point of vanishing. Dragonfly 44 is one of these. It has stars. They're just spread out like that continent of streetlights. The stars are real. They're simply diluted. The second kind is something even stranger, and it's the one that gives tonight's story its title. It's called a dark galaxy. And a true dark galaxy isn't just a galaxy with faint spread-out stars. It's a galaxy that seems to have barely made any stars at all. Almost none. A dark galaxy is a great cloud of gas, and something else, something invisible, we'll get to in a moment, that somehow never lit up, never caught fire into starlight the way a normal galaxy does. If an ultra-diffuse galaxy is a town whose lights are scattered thin, a dark galaxy is a town where the lights were somehow never switched on at all, and yet the buildings, the streets, the weight of the whole place are all still there in the dark. So keep those two apart in your mind, gently, ultra-diffuse, stars but spread thin. Dark galaxy, the starlight essentially absent altogether. The title's promise, barely a star to show, actually fits both of them in their own ways. But they get there by very different roads, and the difference between them is going to matter a great deal before the night is over. Now, I mentioned something invisible, something that's there even when the stars are not. This is the deepest part of the mystery, and I'll introduce it softly. When astronomers weigh these galaxies, when they measure how much stuff is actually in them by watching how their gravity behaves, they find far, far more mass than the stars could ever account for. There's something heavy in there, something that has weight, that pulls on things, that holds the whole structure together, and yet gives off no light of its own that we can see. We call this dark matter. Not dark as in evil, not dark as in sinister, dark simply as in unseen. Invisible mass. Something that seems to make up a great deal of the universe, and yet has never been directly seen, only felt through the tug of its gravity. And I want to be very careful here, because this is exactly where the muddle happens. Dark matter and dark galaxy are not the same phrase, even though they share that word. Dark matter is the unseen mass, the invisible stuff that has weight but gives off no light. A dark galaxy is a galaxy without visible starlight. One is a substance, the other is an object. A dark galaxy might be made mostly of dark matter, yes, but they are different concepts, and slurring them together is the single easiest way to get lost tonight. So we'll keep them separate, carefully, like two candles set a little apart, so their flames don't blur into one. All right. Take a slow breath. We've laid the foundation. We know these ghostly galaxies exist. We know they're faint beyond belief, dimmer than the glowing air. We know there are two kinds, the diluted and the truly dark. But that leaves the most wonderful question of all still hanging in the quiet. If a galaxy is fainter than the empty sky, if its stars are so few and so spread out that our best optical telescopes look straight through it, then how on earth do we know it's there at all? How do you find something that is, for all practical purposes, invisible? And the answer is one of my favorite things in all of science, because it turns astronomy from something you only do with your eyes into something you do, in a way, with your ears. Here is the trick. Even a galaxy with almost no stars is not truly empty. It's full of gas. Specifically, it's full of hydrogen, the simplest and most common substance in the entire universe, the very first element that ever existed. A single hydrogen atom is about as basic as matter gets. one proton at the center and one electron whirling around it. That's the whole thing. And that lonely little electron, in its most settled, restful state, does something quietly magical. Every so often, on its own, without any prompting, it flips. There's a property of both the proton and the electron, a kind of tiny internal orientation that physicists call spin. And you can picture it, loosely, as each of them having a little arrow that points either the same way as its partner or the opposite way. When the atom relaxes from the arrangement where the arrows point the same way into the one where they point opposite, it releases a tiny, tiny puff of energy. A whisper. And that whisper comes out as a radio wave. Not visible light. Not something your eyes could ever catch, a radio wave with a very particular, very precise wavelength. That wavelength is 21 centimeters, about the length of your hand, from wrist to fingertip. And its frequency, the pitch of this cosmic note, if you like, is a very exact number, 1420.405 megahertz, written more roughly 1420 megahertz. That is the sound, if we can call it that, of neutral hydrogen quietly settling in the dark. Now, for any single atom, this flip is an extraordinarily rare event. A given hydrogen atom might wait millions of years before it happens, but space is vast, and a galaxy holds an almost unthinkable number of these atoms, so many that even though each one is patient beyond imagining, at any given moment, countless numbers of them are flipping, all across the cloud, sending out their little 21-centimeter whispers. Add up all those whispers, all across a galaxy, and it becomes a hum. A steady, faint radio glow that pours out into space. It's called the 21-centimeter line, or sometimes just the hydrogen line. And astronomers who study it often refer to that neutral atomic hydrogen by a shorthand, Hi, spoken as H1. And this is the beautiful part. A cloud of hydrogen glows in this radio band, whether or not it has ever made a single star. The gas sings at 21 centimeters, all on its own. So a galaxy can be utterly dark to the eye, invisible in every optical telescope we own, and yet be humming away, loud and clear in the radio. The telescope sees nothing, and the radio dish hears it singing. To catch that singing, we've built some truly magnificent instruments. There was Arecibo, that enormous dish, nestled into a natural bowl in the hills of Puerto Rico, for decades one of the greatest radio ears humanity ever built. There's the very large array in the New Mexico desert, a great spread of dishes arranged like a giant Y across the flat land, working together as one. There's the Green Bank Telescope, an immense white structure standing in a quiet valley in West Virginia, in a specially protected zone, kept free of radio interference so it can listen to the faintest cosmic murmurs. There's Westerbork, a line of dishes out in the Netherlands, and there's FAST, in China, the 500-meter aperture spherical telescope, the largest single dish of them all, another great bowl set into the landscape, listening to the sky. These are the instruments that map hydrogen where the eye sees only black. They draw pictures of galaxies that no camera could ever photograph, painting them not in light, but in the radio glow of their gas. And I have to tell you one more thing about this 21-centimeter signal, because it's the kind of detail that makes me feel very tender toward our strange, curious species. This particular frequency, this note that neutral hydrogen sings, is so fundamental, so universal, that we chose it to speak for us to the stars. When we launched the Pioneer spacecraft and later the two Voyager probes out beyond the planets and into interstellar space, carrying their famous plaques and golden records meant as messages to any mind that might one day find them, we engraved this hydrogen transition on them. We used the 21-centimeter wavelength as a kind of universal ruler, a unit of length and time that any advanced civilization anywhere in the cosmos would recognize, because hydrogen is everywhere and it sings the same note no matter who is listening. So the very same signal we use to hunt for invisible, nearly starless galaxies drifting in the dark is the signal we chose as humanity's cosmic calling card. The whisper of the simplest atom in existence. It's the ruler we measure ghosts with, and it's the greeting we sent out into the night on behalf of everyone who has ever looked up and wondered. There's something in that pairing that I find almost unbearably lovely. The same soft radio note that betrays a hidden galaxy also carries our hello to the stars. I hope you're still comfortable. I hope, if anything, you're a little more relaxed than when we began. The way you can sink deeper into a chair when a story settles into its rhythm. We don't need to rush any of this. The hydrogen has been humming for billions of years. It can wait for us to get there slowly. Let me gather up where we are, gently, before we go deeper. Because in the parts to come, we're going to walk right up to these objects one by one and look at them closely. We've met the idea of a galaxy that is nearly empty of stars, a galaxy the size of our own Milky Way, holding only 1/100th as many suns, hanging out there in the Coma Cluster 320 million light-years away, discovered by Van Dokkum and Abraham and their team back in 2015. We've learned why such a thing can hide from us, because surface brightness, how thinly the light is spread, is what makes a galaxy vanish, and these galaxies are spread so thin they sink below the faint natural glow of our own night sky, down into that strange realm of 24, 25, 26 magnitudes per square arc-second, fainter than the airglow overhead. We've drawn the careful line between two different sorts of ghost, the ultra-diffuse galaxy that truly has stars but wears them thin, and the dark galaxy that seems to have barely lit any stars at all. And we've learned the wonderful secret of how you find something invisible. By listening for the 21-centimeter song of neutral hydrogen at 1420 MHz, the same note engraved on our Voyager and Pioneer plaques, caught by great dishes like Arecibo and the Very Large Array and Green Bank and Westerbork and FAST. Now there's a question sitting underneath all of this, and I want to name it now so it can quietly work on you as we drift onward. The way the best questions do, half answered in your mind as you fall asleep. It's this. If a galaxy can exist with almost no starlight, then which is it, really? Did it never manage to make its stars in the first place? Or did it make them and somehow lose them? Did the lights never turn on? Or did they turn on and then go out? That question, that simple-sounding, bottomless question, is going to lead us into some genuinely strange and unresolved territory, into a debate that real astronomers are still honestly having with each other right now. Because here is where the story stops being simply a tale of wonder and becomes something with a real edge to it, a real mystery that isn't tied up neatly. When you go to weigh a galaxy like Dragonfly 44, when you carefully measure how much total mass it must contain to behave the way it does, you find something that ought to be impossible. You find that the stars, that faint 1% sprinkle of starlight, account for almost nothing of its weight. The overwhelming majority of the galaxy, the vast bulk of what holds it together, is that invisible dark matter we spoke of, the thing you cannot see. In the headline measurement of Dragonfly 44, the fraction came out staggeringly high, so high that the stars started to look like little more than a rumour scattered across a great dark cloud. A galaxy that is almost entirely darkness, with barely a star to show. And how? You might reasonably ask, how could anyone possibly measure the weight of something they cannot see? How do you put a nearly invisible galaxy on a scale? That is exactly where we're headed next, into the clever and patient methods astronomers use to weigh a ghost, and into the surprising, honest fact that even the famous numbers we started with tonight, that dramatic figure for how dark Dragonfly 44 truly is, would later be questioned and revised by the very people who found it. Because that's how real science works, slowly, carefully, always willing to go back and check its own arithmetic. There's a beauty in that too, I think, a quiet humility running underneath all the wonder. Quick reminder before we go on, and I'll keep it brief. After years of my own of lying awake with a racing mind, sleep that actually goes deep finally became possible for me. Now the learning comes easier, the energy is real, the mind stays sharp through the day. Sleeping like a baby honestly changed everything. If you'd ever want the exact system that made that possible, it's in the link in the pinned comments. That's all. Just something I've found that I wanted to leave quietly here for you. So let's carry on. Softly, picture Dragonfly 44 again, hanging in the black of the Coma Cluster, that great faint disk you could never photograph in any ordinary way, so dim it hides beneath the glow of empty air. And now imagine standing before it, with the impossible task of weighing it, of asking the universe gently, how much do you really contain? Not how bright are you? How heavy are you? Because those two things, for these galaxies, turn out to be almost completely unrelated, and the gap between them, the enormous gulf between the little light and the great weight, is the whole heart of the mystery we're wandering into. The way you begin to answer it is not by looking at the stars themselves, but by watching how they move. And that motion, the quiet, patient dance of the few stars a dark galaxy does have, is about to tell us something that has kept astronomers arguing and wondering for years. But before we follow those stars, let me say one warm thing, and then I'll let you sink back into the dark. If you found some comfort here, in this slow drift through the invisible, a gentle like and a subscribe genuinely help this sleepy little channel keep going. Small creators like me really do rely on it, more than you'd think. And to those of you already here, already returning night after night, thank you. Truly, you make this quiet room feel a little less empty. So tell me, if you like, down in the comments, where in the world are you listening from tonight? And what time has it gotten to in your corner of the dark? I always love to imagine you all out there, scattered across the turning earth, some of you just now closing your eyes. And you don't have to stay awake for any of this. That's the whole point. If you drift off somewhere in the middle of a sentence, the galaxies will still be here, patient as they've always been, waiting in the same black they've floated in for billions of years. You won't miss anything you can't find again. So let your shoulders go heavy. Let the pillow take the full weight of your head. We'll go slowly, and there's nothing you need to hold on to. Now, that impossible task of weighing a galaxy you can barely see. To understand why it's so hard, we have to talk for a moment about how you even find one of these ghosts in the first place. Because it turns out that hiding, for a galaxy, is embarrassingly easy. You'd think a thing the size of the Milky Way would be impossible to overlook. But brightness, real brightness, the kind that catches a telescope's eye, depends not just on how much light a thing gives off in total, but on how tightly that light is packed together. Astronomers have a name for this. They call it surface brightness. It's the light per little patch of sky, and it is everything. Think of it this way. Take a single candle in a dark room, and it's easy to see. Now take that same amount of candlelight and smear it across an entire wall, thin as breath, and suddenly you can barely tell the wall is glowing at all. The light is still there, every last photon of it, but spread so wide, so gently that your eye slides right past it. That is exactly what happens to an ultra-diffuse galaxy. It might have a real population of stars, genuine suns, but they're scattered so thinly across such an enormous space that the whole thing fades into almost nothing. And here is the detail that always stops me. Many of these galaxies have a central surface brightness, somewhere around 24 to 27 magnitudes per square arcsecond. Now those are just numbers, and I don't want you doing arithmetic half asleep, so let me tell you what they actually mean. Because it's genuinely strange. It means the brightest heart of these galaxies is fainter than the natural glow of Earth's own night sky, fainter than the air above you. Because our atmosphere is never truly dark. There's a soft, perpetual shimmer called airglow, molecules high up releasing tiny breaths of light, and it means the sky itself is quietly luminous, even on the blackest, moonless night far from any city. So to find one of these galaxies, you are looking for something dimmer than empty space appears to be. You are hunting a shape that is fainter than the nothing it sits behind. For decades, that's why we simply didn't see them. They were there the whole time, drifting overhead, softer than the darkness. Now I've been using two phrases a little loosely, and I want to gently pull them apart, because the difference matters, and getting it right is part of what makes this beautiful, instead of just confusing. I've said dark galaxy, and I've said ultra-diffuse galaxy, and they are not the same thing. Let me lay them side by side slowly. An ultra-diffuse galaxy, like Dragonfly 44, does have stars. Real ones. It's just that they're diluted, spread out over a Milky Way-sized stretch of space when there are only about a dwarf galaxy's worth of them, perhaps 1,000 times fewer than our own galaxy holds. So it's dim, achingly dim. But it is a galaxy of genuine starlight, simply watered down until it nearly vanishes. It has stars to show. Barely, but it does. A true dark galaxy is something stranger still. It's a halo of gas and dark matter that, as far as we can tell, never managed to make a meaningful population of stars at all. The starlight isn't diluted, it's essentially absent. The gas gathered, the invisible mass gathered, and then, for reasons we're still trying to understand, the lights never came on. A galaxy that forgot or was never able to ignite. Those are the real ghosts, and they are far, far harder to find, because you cannot look for their starlight. There isn't any to look for. Which raises the obvious, wonderful question. If a galaxy gives off no starlight, how could you ever know it's there at all? How do you photograph a thing that emits no visible light? And the answer, when I first understood it, gave me the loveliest shiver. You don't look, you listen. Because even a cloud of gas with not a single star in it is not truly silent. It's made largely of neutral hydrogen, the simplest, oldest, most abundant stuff in the whole universe. A single proton with a single electron drifting around it. And every so often, on its own quiet schedule, that atom does something almost imperceptibly small. The electron flips, it changes its orientation, ever so slightly relative to the proton, and in doing so it releases a tiny whisper of energy, a radio wave with a wavelength of exactly 21 centimeters, about the length of your hand. One atom doing this is nothing. You'd never notice. But gather enough hydrogen together, a whole galaxy's worth, uncountable trillions upon trillions of atoms, and all those tiny flips add up into a steady, faint hum. A note the universe sings at a frequency of 1420 megahertz. Optical telescopes see empty black. But point a radio dish at that same patch of sky, and you hear it, a galaxy, singing softly in hydrogen, exactly where your eyes swore there was nothing. This is the 21-centimeter line, and it is one of the most important sounds in all of astronomy. It's how the great radio observatories, Arecibo before it fell, the very large array out in the New Mexico desert, Green Bank, Westerbork in the Netherlands, and the enormous dish called Fast Nestled in the hills of China go looking for what light cannot show them. They map the invisible hydrogen, tracing galaxies by their radio glow, drawing the shape of things that never lit a single star. And it was one of those maps, drawn not from light but from radio whispers, that eventually led astronomers toward a name that sounds almost like it belongs in a fairy tale. Dragonfly 44. You'll remember we met it briefly, right at the start. A galaxy sitting in the Coma Cluster, about 320 million light-years away, roughly the same width as our own Milky Way, and yet holding only something in the neighborhood of 1% of its stars. We established the size. We established the scarcity. But we haven't yet sat with the full strangeness of it. And that strangeness, when you let it settle properly, is one of the more quietly unsettling things I think astronomy has given us in recent years. So let's stay here for a little while. Let's get comfortable with Dragonfly 44 and see exactly what it is that makes it so strange and how we even began to know what it was. Because the story starts not with a massive telescope on a mountainside, but with something you might find in a photography shop. The Dragonfly Telephoto Array is the instrument responsible for finding Dragonfly 44, and when you first learn what it is, you might assume someone is gently pulling your leg. It is, in essence, a collection of Canon telephoto camera lenses. Consumer optics. The kind used for wildlife photography or sports events or catching the moon rising over a distant tree line. Bolted together, aimed at the same patch of sky, combined into something that behaves as a single low-surface brightness detector. It was conceived and built by Pieter van Dokkum and Roberto, and the idea behind it was genuinely elegant in its simplicity. Big telescopes are wonderful at finding faint point sources, single stars, distant quasars, objects that concentrate their light into a tiny dot. But ultra-diffuse objects, things that spread their extremely faint light across a large area of sky, are almost harder for a large mirror to see than a small one. The issue is a thing called sky background. The atmosphere itself glows faintly, a kind of natural light pollution called airglow. And so does the accumulated glow of faint distant galaxies below the telescope's resolution. Every telescope sees its target against this background noise. If your target is much fainter than the background, it drowns. Large telescopes, with their intricate optics made of many reflecting surfaces, can scatter and spread that background light in ways that mask the exact kind of extended, gossamer thin surface brightness you're trying to detect. A simpler optical system with fewer internal reflections and a very clean light path handles scattered light better. and camera lenses designed for photographers who care deeply about not having blurry edges or artifacts across a wide field turn out to be remarkably clean in exactly this way. So Van Dokkum and Abraham assembled an array of these lenses, pointed them at the Coma Cluster in 2015, and in the images they produced, things emerged that no one had seen before. Ghosts in the data. Enormous, barely there smudges, spread thin as breath on cold glass, scattered through and around one of the richest galaxy clusters in the nearby universe. And among them, faint but real, was the object that would become the centerpiece of the whole conversation. The one they eventually catalogued as Dragonfly 44. Now, the Dragonfly Telephoto Array could tell you it was there. It could tell you it was large and faint and roughly oval. What it could not tell you was how much it weighed. And that was the number that mattered most, because size, as we've already seen tonight, tells you almost nothing about a galaxy's true nature. What matters is what it's made of, how much dark matter is holding it together. Whether the stars you can see are the whole story or just the faint footnote at the end of a much bigger book. For that, you need to measure the motion of those stars. Here's the intuition. And it's worth settling into this carefully, because this technique is one of the workhorses of modern astrophysics, and it shows up again and again every time we try to weigh something invisible. Close your eyes for a moment and imagine a pot of boiling water. The water molecules in that pot are moving, bouncing off each other, travelling in all directions at once, fast and chaotic. The hotter the water, the faster they move. Now imagine that instead of a pot of water molecules, you have a swarm of stars inside a galaxy, all moving under the influence of gravity. They're not orbiting in neat circles, not like planets around a sun. They're moving in a kind of complicated three-dimensional dance, pulled this way and that by every other mass in the system. Some of the stars in your swarm are moving toward you at any given moment. Some are moving away. Most are somewhere in between. If you point a spectrograph at that swarm, you can measure the Doppler shift of the starlight. Stars moving toward you have their light compressed to slightly shorter wavelengths, shifted toward the blue. Stars moving away have their light stretched to slightly longer wavelengths, shifted toward the red. And because all these stars are moving in different directions at different speeds, the absorption lines in the spectrum you record are not a single crisp line, but a broadened smear, the sum of all those tiny blue and red shifts at once. The width of that smear, how broad it is, tells you something crucial. It tells you the range of speeds the stars are moving at. That range is called the velocity dispersion. And here is the key step. The velocity dispersion of a gravitationally bound system is related to the total mass of that system. Think of it this way. If you have a very massive gravitational well, things falling into it and orbiting within it move fast. They have to stay in orbit, the way a satellite in low Earth orbit has to move at nearly 8 kilometers per second just to keep from falling down. The deeper the well, the faster the motion. So a high velocity dispersion implies a large total mass. A low one implies a small mass. You measure how fast the stars are moving, you apply the physics, and you infer the mass of everything that's making them move, whether you can see it or not. This technique has a long and productive history. It was the same kind of reasoning applied to galaxies moving inside clusters that led Fritz Zwicky all the way back in the 1930s to conclude that there must be far more mass in the Coma Cluster than he could account for with visible stars and gas alone. He called it Dunkelmaterie, dark matter, and it was a measurement of stellar velocities inside individual galaxies that, Decades later, in the 1970s, led Vera Rubin and Kent Ford to confirm that even within a single spiral galaxy, stars at the outer edges are moving far too fast to be explained by the visible mass alone. The dark matter interpretation has been supported by motion ever since. So in 2016, the year after Dragonfly 44 was discovered, Pieter van Dokkum's team pointed the Keck telescope at it. Keck, with its enormous 10-meter mirror on the summit of Mauna Kea in Hawaii, is a very different instrument from a Canon lens array. Where the Dragonfly is optimized for catching faint, diffuse light across wide angles, Keck is optimized for gathering as much light as possible from a small area and dispersing it with extraordinary precision. The spectrograph used for this observation was DEIMOS, the Deep Extragalactic Imaging Multi-Object Spectrograph, and the measurement took many hours of collecting starlight across multiple nights. What they found, when the data came back, was a velocity dispersion of around 47 kilometers per second. Pause on that for a second. That's the average spread of speeds among Dragonfly 44's stars. Each star moving at its own particular velocity through that dark, diffuse system, contributing its own tiny Doppler shift to the blend, and together they add up to a dispersion of 47 kilometers per second. Not fast by stellar standards, not alarming in isolation. But when you put that number into the equations, when you ask what total mass is required to keep a system of stars moving like this, bound together and not flying apart, the answer is startling. The inferred total mass of Dragonfly 44 from that velocity dispersion came out at around 1 trillion solar masses, 10 to the power of 12. A number so large, it requires a moment of just sitting with it. 1 trillion suns worth of gravitational pull, all concentrated in a system that optically looks almost empty. And the stars account for roughly 1% of that, maybe a little less, which means that the remaining 99%, and this was the figure that appeared in the headlines in 2016, roughly 99.99% of Dragonfly 44's total mass is dark matter. The stars, for all that they're the only part you can see, for all that they're the only reason you know the thing is there at all, are barely relevant to the gravitational accounting. They are rounding error. The galaxy is, by mass, almost entirely made of darkness. Now, I want to be careful here in the way good science demands, because the number I just gave you, the 99.99%, is the headline figure from the 2016 paper, and it made Dragonfly 44 famous almost overnight. But there is a revision, a meaningful one, and I don't want to tell you only half the story. In 2019, Van Dokkum's own team returned to Dragonfly 44 with better and deeper observations. More time on sky, more data, more careful treatment of the measurement uncertainties. And the revised velocity dispersion they found was lower than the 2016 estimate. Around 33 kilometers per second instead of 47. That's not a small difference. Velocity dispersion feeds into the mass estimate in a sensitive way, roughly as the square, so bringing the dispersion down from 47 to 33 kilometers per second pulls the total inferred mass down considerably. The headline dark matter fraction was revised downward. Dragonfly 44 is still an object dominated by dark matter. Still a genuinely strange and scientifically important system, still far, far more dark than bright. But the absolute extremity of the 2016 claim that it is essentially a perfect dark matter galaxy with stars reduced to the merest ornament was softened somewhat by the 2019 result. The honest picture is this. Dragonfly 44 is a system that appears to be very heavily dark matter dominated. A fact well supported even after revision, but the precise fraction is uncertain, and the initial number, the one that went around the world, was revised. This is what science is supposed to do. Measure, revise, be honest about uncertainty. The galaxy is still extraordinary. The measurement is just a little less extreme than first advertised. I think it's worth noting, before we go on, that this kind of revision is not a sign that something went wrong. It's a sign that something went right. The team that published the dramatic 2016 result was the same team that came back 3 years later and said, "Wait, let's look again, let's be more careful." That's not a failure of science. That's science working exactly as it should, and I find it quietly reassuring in a world where we're often asked to treat initial results as final truths. They aren't. They rarely are, in any discipline. Dragonfly 44 is still remarkable. Its story is just a little more nuanced, a little more honest than the version that made the news. But let's stay with the question of how you know what Dragonfly 44 is. Because the velocity dispersion, even revised, leaves room for uncertainty. You're looking at a very faint object, very far away, with a relatively small number of detectable stars, and you're trying to infer the total mass of something you can't directly see. The measurement is difficult. The error bars are real. And astronomers know this. So they turned to a second, independent line of evidence. One that doesn't rely on the velocity of stars directly, but instead uses a kind of cosmic counting exercise. And this is where Dragonfly 44's globular clusters enter the story. Globular clusters. The name conjures something ancient, which is accurate. They are spherical collections of stars, tens of thousands to millions of stars, packed tightly together, orbiting the outskirts of galaxies like old retainers in a manor house. The Milky Way has around 150 of them, maybe slightly more, depending on how you count. They are among the oldest objects in the universe, formed in the earliest epochs of galaxy assembly. Their stars dating back sometimes to within 1 billion years of the Big Bang. They glow blue-white and ancient, little spheres of compressed light drifting in the halos of galaxies. And over the years, as astronomers catalogued globular cluster populations around more and more galaxies, a striking pattern emerged. The number of globular clusters a galaxy hosts is correlated, not perfectly, but robustly, with the total mass of its dark matter halo. Not with its stellar mass. Not with the brightness you can see. With the total halo mass, the full gravitational well, including all the invisible dark matter. More precisely, it scales with the total halo mass in a way that has been confirmed across galaxies ranging from dwarfs to giant ellipticals. It's not entirely understood why this relationship exists. The leading ideas involve globular clusters forming preferentially in the deepest, most massive gravitational concentrations during the early universe, and surviving better in large halos than small ones. The exact mechanism is still debated, but the empirical relationship is well established enough that astronomers now use globular cluster counts as what they call a mass tracer, an independent way of estimating a galaxy's halo mass without needing to measure the motion of its stars. Think of it like this. If I tell you a house has 16 bathrooms, you can make a reasonable inference about how large the house is, even if you've never seen it. The number of bathrooms doesn't cause the size, but it correlates with it well enough to be useful. Globular clusters are, in a rough sense, the bathrooms of the galaxy world. A galaxy with many globular clusters is almost certainly sitting inside a very large dark matter halo. And Dragonfly 44 has a lot of globular clusters. An unusually rich swarm of them, far more than you would expect from a galaxy with so few stars. The Hubble Space Telescope was brought in to count them, peering at the faint extended halo of Dragonfly 44 and resolving the individual point sources that cluster around it. And the count that emerged was consistent with a very massive galaxy, a galaxy whose total halo mass is large. Not a lightweight debris field or a stripped dwarf, but something that once had, and perhaps still has, the gravitational architecture of a genuinely substantial system. This is important because it provides a check. The velocity dispersion and the globular cluster count are two entirely different measurements, using two entirely different physical relationships, and they broadly agree with each other in the direction they point. Both suggest that Dragonfly 44 is a massive object, dark matter dominated, sitting inside a halo far larger than its stellar content would lead you to expect. Neither measurement is perfect. Both carry uncertainties. But the convergence between them is a meaningful signal. When two independent methods point the same way, the confidence in the conclusion rises. The question the globular clusters raise, as well as partly answering, is how a galaxy could end up in this state. Massive halo, very few stars, far out in the Coma Cluster, glowing so faintly it was invisible until a cluster of camera lenses found it. That is not what a galaxy is supposed to look like, at least not according to our standard picture of how galaxies form. In the ordinary story, the one most astronomers still believe in its broad outlines, even if the details are being constantly revised. Dark matter clumps together first. Pulled by gravity into large, roughly spherical halos. Gas, ordinary matter, hydrogen and helium, falls into those halos and pools at the center. The gas cools because cooling gas loses energy, and as it loses energy it falls further in, densifying until eventually some of it becomes dense and cold enough for self-gravity to take over and collapse it into stars. Stars form. More stars form. The halo lights up. A galaxy is born. That is more or less what happened to every normal galaxy. It's what happened to the Milky Way. It's what happened to the Andromeda Galaxy, and to the hundreds of billions of other galaxies we can see scattered across the universe. The dark matter provided the architecture, the gas provided the fuel, the stars lit up in their halos, and the universe became visible. But what if the gas never cooled? What if it was stripped away before it could condense? What if the halo formed, but something, some environmental catastrophe, some early feedback from the stars that did form, prevented most of the star forming from ever happening? Then you'd end up with a massive halo and barely any stars. You'd end up with something that looks, from a great distance, like a ghost. Like Dragonfly 44. We're going to come back to the question of why and how in more detail a little later in our journey tonight. There are competing theories and they're all interesting. But I want to park that question here, like a breadcrumb left at a fork in a forest path, and let it sit quietly in the back of your mind while we turn to examine the galaxy from another angle. Because there's something else about Dragonfly 44 that sits just beneath the surface of the conversation. Something that connects the specific strangeness of this one object to a much larger, older, stranger question about the nature of what makes up most of the universe. When astronomers say that Dragonfly 44 is almost entirely dark matter, they mean that the thing making it behave the way it does, the thing bending its stars into their orbits, the thing keeping it from flying apart, is something that neither emits nor absorbs nor reflects electromagnetic radiation. It is not gas. It is not dust. It is not dim stars or black holes or any kind of ordinary matter we know how to point a telescope at. It is something that interacts with the rest of the universe through gravity and, as far as we can tell, through gravity alone. We have never caught a single particle of it directly. We have never held it, weighed it, touched it. We infer it from the way it moves other things, the way a strong wind is invisible until it bends the trees. The honest position, the position that the evidence actually supports, is this. Dark matter is the leading explanation for a large and consistent set of observations, from the velocities of stars in galaxies to the velocities of galaxies in clusters, to the way light bends around massive objects, to the patterns in the temperature fluctuations of the cosmic microwave background, which is essentially a photograph of the infant universe. All of these point in the same direction. All of them are explained with impressive precision by a cold dark matter model in which about 27% of the universe's total energy density is in this invisible gravitating stuff. The model works. It predicts things, and those predictions come true. That is the strongest endorsement physics can give. And yet, we have never seen a dark matter particle in a detector. The elegant experiments buried deep underground, shielded from cosmic rays, watching for the faintest recoil of a single atom, have come back empty, year after year. The candidate particles, predicted by the most popular theoretical extensions of the standard model of particle physics, the weakly interacting massive particles, the WIMPs, have so far declined to show up. The search continues, but the simplest, most obvious candidates have not appeared where we expected them. That is uncomfortable. It doesn't invalidate the gravitational evidence, which is robust, but it does mean there is an open question about what dark matter actually is. Dragonfly 44 sits in the middle of this question like a question mark made of stars, or almost stars. A system so thoroughly dominated by dark matter that it gives you a way to study the stuff in near isolation, to ask how a dark matter halo behaves when the contaminating influence of a normal stellar population is reduced almost to nothing. It's a kind of natural experiment, a galaxy that stripped itself down to near elemental simplicity and left the dark matter almost naked. And that nakedness, strangely, makes Dragonfly 44 an important object. Not just an interesting one, an important one. Because if you want to understand dark matter, you want to find places where it dominates overwhelmingly, where its effects are large and clean and hard to confuse with anything else. A place like Dragonfly 44. Let's stay with the velocity dispersion for another moment, because I think it rewards a second look from a slightly different angle. Imagine you're standing in a dark field on a clear night, far from any city, and you're watching a swarm of fireflies. Not one or two, but hundreds of them, all moving in different directions, blinking softly in the dark. Some are moving toward you, getting brighter and slightly bluer in their light. Some are moving away, getting dimmer and slightly redder. You can't follow any individual firefly with your eyes. The motion is too complex, too tangled. But if you took a long exposure photograph of the whole swarm, the combined light of all those moving bodies would form a certain kind of blur. And from the shape and width of that blur, you could, with the right physics, estimate how energetically the swarm was moving. And from the energy of the swarm, if you knew how big the swarm was, you could infer how deep the gravitational well must be to keep the fireflies from flying away into the night. That's essentially what the DEIMOS spectrograph on Keck did to Dragonfly 44. It collected the combined light of hundreds of stars simultaneously, recorded their Doppler shifts all at once in a single spectrum, and measured the broadening of the absorption lines. The width of that broadening is the velocity dispersion, and the velocity dispersion is the key to the mass. The 47 kilometers per second from 2016 revised to 33 in 2019. Both measurements pointing to something massive, both measurements pointing toward a halo of dark matter far larger than the visible stars could account for. And then the globular clusters counted patiently from orbit with Hubble, adding their independent voices to the same conclusion. An unusually rich population, more of them than you'd expect from a simple small galaxy, consistent with the deep, heavy halo that the stellar velocities implied. Two methods, two independent physical relationships, two arrows pointing the same direction. Dragonfly 44 is not something small and lightweight that happened to find itself in a sparsely starred corner of the Coma Cluster. It is, the evidence suggests, a genuinely massive system. A galaxy that was always meant to be large, that has the architecture of a large galaxy, the dark matter scaffold of a large galaxy, and yet somehow arrived in the present universe without ever managing to fill that scaffold with stars. It's as if someone built a cathedral and then neglected to install the light. The Coma Cluster, where Dragonfly 44 lives, is itself worth pausing on. It's one of the largest and most studied galaxy clusters in the nearby universe, a city of thousands of galaxies bound together by their collective gravity, sitting about 320 million light-years away in the direction of the constellation Coma Berenices. It is an extreme environment. The space between the galaxies in a cluster like Coma is not empty the way deep intergalactic space is empty. It's filled with hot, sparse, X-ray emitting gas, the intracluster medium, a plasma at temperatures of tens of millions of degrees. Things moving through that plasma feel a wind, a gentle but persistent headwind of hot gas that can, over time, sweep ordinary gas out of a galaxy the way wind strips leaves from a tree. Ram pressure stripping, this process is called. A galaxy moving through the cluster at high speed can lose its cold gas reservoirs, the fuel for new stars, in a cosmic eye blink. A few 100 million years, which is not very long in galaxy terms. It's one of the reasons astronomers thinking about Dragonfly 44 and its kind have wondered whether the Coma Cluster environment itself is part of the explanation. Perhaps these objects had more stars once, more gas, more ongoing star formation, and the cluster stripped it away. Or perhaps they fell into the cluster environment very early, before they ever had a chance to accumulate cold star-forming gas in the first place. The environment doesn't just host these galaxies, it may have shaped them into what they are. But here is what I find most compelling about the Dragonfly 44 story, and what I want to leave you sitting with as we prepare to turn toward the next chapter of tonight's journey. The galaxy is, by its nature, a challenge to our intuitions about what a galaxy is. We grew up, scientifically speaking, looking at a universe full of glowing things. Stars, nebulae, the luminous spiral arms of galaxies wheeling through the dark. We built our understanding of how galaxies form and evolve almost entirely from the things we could see. And seeing, in astronomy, is a very particular and limited kind of knowledge. We see light. We see stars and the gas they illuminate. We see the bright face of the universe. But Dragonfly 44 is a reminder that the universe also has a dark face. a gravitational architecture that doesn't necessarily correspond to luminous content. A halo can exist without lighting up. A scaffold can stand without being filled. And we can spend decades staring at the sky with beautiful, expensive optical telescopes and never know that a system like this is there, sitting quietly in the Coma Cluster, holding the gravitational weight of 1 trillion suns, invisible to everything except a careful pair of camera lenses and a patient radio dish. There is something almost meditative about that. The universe is not obliged to make itself visible to us. Most of it isn't. And the objects that challenge us most, the ones that demand we develop new tools, new techniques, new intuitions, are often the ones that ultimately tell us the most about the deep structure of things. Dragonfly 44 is one of those objects, uncomfortable in the best possible sense. Before we move on to the next character in our story tonight, because there are others waiting, each strange in its own particular way, I want to mention one small thing about the Dragonfly Telephoto Array that I find quietly delightful. The instrument that found Dragonfly 44, that found 47 ultra-diffuse galaxies in a single survey of the Coma Cluster, that opened up a whole new window onto the faint diffuse universe, was built not from custom-designed space-age optics, but from commercially available camera lenses. Consumer technology, the sort of thing a photographer might pack into a bag for a wedding shoot or a wildlife expedition. Van Dokkum and Abraham looked at the problem they needed to solve, the need to catch faint extended light with minimum internal scattering, and realized that the solution was already sitting on a shelf in a camera shop. They just needed a lot of them, pointed together, working in concert. There's something in that, I think, about the way science actually works. Not always through the biggest, most expensive, most elaborate instruments, but sometimes through a clear-eyed understanding of what the problem actually requires. And the willingness to reach for an unexpected tool. The Canon telephoto lens has, in its way, done more for our understanding of the hidden universe than many a purpose-built behemoth. And that seems worth mentioning, quietly, before we let Dragonfly 44 drift back into its faint corner of the Coma Cluster and turn our attention elsewhere. Because while Dragonfly 44 was being weighed and counted and argued over, the conversation around dark galaxies and ultra-diffuse galaxies was not standing still. Far from it. The universe, with its customary stubbornness, had another surprise waiting. Not a galaxy stuffed full of dark matter. Not a galaxy with a massive halo and barely any stars. The opposite. A galaxy, a real, extended, recognizable galaxy with globular clusters and a measured velocity dispersion and a distance estimate and everything else you'd expect that appeared to have almost no dark matter at all. A galaxy that, if the measurements were right and the distance was right, was made almost entirely of the visible, ordinary stuff. Stars and gas and dust and nothing else. No invisible halo. No dark scaffolding. Just matter. Plain matter. In a universe where we had been told for decades that plain matter was only the minority, the pale fraction, the thin, bright skin on a deep, dark ocean. That discovery, and the fierce, still unresolved debate it sparked, is where we're headed next. But first, close your eyes for a moment if they're not already drifting shut. Let the image of Dragonfly 44 settle. A galaxy as wide as our own, its stars scattered so thin they barely make a dent in the dark. Ancient globular clusters, orbiting in silence through a halo of invisible mass. 1 trillion suns worth of gravity, holding almost nothing you could point to and say, "There, look, that's a galaxy." Just the faint, faint glow, barely brighter than the sky around it, singing quietly in the frequencies of hydrogen and the patient mathematics of moving stars. It's there. It's real. It's one of the stranger things in this strange universe of ours. And knowing it's there, I think, changes something about how the night feels. The darkness outside your window is not nothing. It has structure. It has weight. It just doesn't have the courtesy to glow. And yet, for all that Dragonfly 44 has taught us about what a galaxy can be, enormous and ancient and almost entirely invisible, there is another object, found in a different corner of the sky. In a different kind of quiet, that takes the question even further. Not a galaxy with too few stars spread too thin. Something stranger still. A cloud of hydrogen gas, turning, rotating, holding together with a gravitational grip far stronger than anything its visible contents could explain. And no stars at all. None. Not a few scattered and faint. None that anyone has been able to confirm. Just gas. And mass. And the faint song of the 21-centimeter line ringing out across 50 million light-years of space like a voice in an empty room. Its name is Virgo HI 21. Let that sit for a moment. Virgo, for the galaxy cluster it appears to live in, the Virgo Cluster, one of the great gravitational cities of our local universe, a dense knot of more than 1,000 galaxies bound together by their collective gravity, roughly 54 million light-years from where you're lying right now. High, for neutral atomic hydrogen, the same signal we talked about earlier, the 21-centimeter emission that lets radio telescopes hear what optical telescopes can't see. And 21, simply the designation that was given to it. Not a poetic name. Not a name that tells a story. Just a label, dry and clinical, for something that turned out to be deeply, uncomfortably strange. In 2005, a team led by Robert Minchin, working with data from the Arecibo telescope, that enormous dish, 300 meters across, once the largest single-aperture radio telescope on Earth, announced what appeared to be a detection of a massive cloud of neutral hydrogen sitting in the outskirts of the Virgo Cluster. The cloud itself, as measured in hydrogen, had a mass of around 100 million solar masses. 100 million times the mass of our Sun, in gas alone. That's not nothing. That's a respectable gas reservoir. The kind of material a galaxy might draw on to build its next generation of stars. But here's where it gets strange. When Minchin and his colleagues looked at how that gas was moving, not just sitting there, but spinning, rotating, the way gas in a galaxy rotates around a gravitational center, they found something that didn't add up. The rotation was too fast. Much too fast. The gas was moving in a way that implied a total mass, a total gravitational pull far greater than 100 million solar masses of hydrogen could explain. Their estimate of the total dynamical mass, the mass you infer from how quickly things are moving and how tightly they're being held, came out somewhere in the range of 10 to 100 billion solar masses, 100 to 1,000 times more than the gas alone could account for. Something invisible was doing most of the holding. And that invisible something, in the standard picture, would have to be dark matter. A lot of it. A dark matter halo large enough to be called a galaxy's worth, wrapping around 100 million solar masses of gas, and no stars. No optical counterpart that anyone could find. No glow. No light. Just the rotation, the gas, and the mass implied by the math. If that interpretation is right, Virgo HI 21 is the cleanest example of something we have been calling a dark galaxy. Not an ultra-diffuse galaxy with a few faint stars, not Dragonfly 44 with its sprinkle of stellar light and its rich collection of globular clusters. Something more radical. A halo that gathered its gas, held onto it with the grip of billions of solar masses of invisible matter, and yet, for whatever reason, never made a single confirmed star. Or if it did, it made so few of them, so faint, that every telescope we've pointed at that patch of sky has come up empty. A galaxy that forgot to light up. And for a few years after that 2005 announcement, Virgo HI-21 sat in the literature as one of the most promising dark galaxy candidates ever found. The rotation curve was there, the mass discrepancy was there. The radio signal was real and measured and reproducible. All that was missing was a single glowing star. But then, as so often happens in astronomy, and as we've already begun to see tonight, someone looked more carefully, and the story got more complicated. Dust was beginning to settle from the first announcement when another team, led by Pieter Duc and Duc and Bournaud, looked again at Virgo HI-21 and at its surroundings in the Virgo Cluster, and what they proposed in 2008 was a different reading of the same signal. Not a dark galaxy. Not a starless halo rotating under its own gravity. Instead, they argued, what Minchin's team had found was a tidal tail, a long stream of hydrogen gas that had been physically ripped away from a nearby spiral galaxy during a high-speed encounter and left to drift through the cluster, still moving, still carrying the kinetic memory of that violent passage. The nearby spiral in question is NGC 4254, also known as Messier 99. It's a beautiful galaxy, actually, a grand design spiral with sweeping arms, sitting about 50 million light-years away in the Virgo Cluster, not far at all from the position of Virgo HI-21 in the sky. And galaxy clusters, it turns out, are not peaceful places. Galaxies in clusters move fast, sometimes hundreds or thousands of kilometers per second relative to one another, and when two galaxies pass close enough, the tidal forces, the same gravitational stretching and squeezing that gives us ocean tides, but on a vastly grander scale, can pull long streamers of gas off the outer disks of both galaxies, flinging hydrogen into intergalactic space in long, curling filaments. Duc and Bournaud's argument was essentially this: Virgo HI-21 is not a separate object with its own gravitational halo. It's one of those tidal streamers, a slab of gas that was yanked off Messier 99 during some past gravitational encounter and is now drifting and tumbling in the space between galaxies. And the rotation that made it look like a galaxy in the original measurements, the orderly velocity gradient that implied a spinning dark matter halo, is not rotation at all. It's the complex internal motion of gas in a tidal tail, moving partly inward, partly outward, in patterns that can mimic the signature of a rotating disk when you look at it from certain angles and at certain resolutions. This is the debate. And it is, genuinely, still open. Not settled. Not resolved. Both sides have made serious arguments with real data. Minchin's team responded to the tidal debris interpretation, and the conversation in the literature continued without producing a clean verdict that everyone accepted. The underlying problem is one of resolution and perspective. The Arecibo observations that detected Virgo HI-21 were looking at it with a radio beam wide enough to blur together all the fine detail in the gas motion. You're seeing a broad, smeared picture of something that might be a rotating disk or might be a twisted ribbon of tidal gas, and distinguishing between those two things with confidence requires either better spatial resolution or additional data that has, so far, not given a clear enough answer to put the debate to bed. So Virgo HI-21 remains on the table. Not proven, not disproven. A cloud of hydrogen in the Virgo cluster, carrying more gravity than its gas alone can explain, with no confirmed starlight and no settled identity. It might be the cleanest, natural, dark galaxy candidate we've ever found. Or it might be the ghost of a spiral arm, torn away from Messier 99 and left to wander. Both of those possibilities are real. Both of them are, in their own way, quietly astonishing. And there's something I want to pause on here before we move forward, because I think it matters. The fact that we don't know which interpretation is right, that's not a failure of science. That's what honest science looks like at its frontier. The data exists. The measurements are real. Two careful teams of astronomers, working in good faith, looked at the same signal and came away with genuinely different readings of what it means. The disagreement lives in the interpretation, in the modelling, in the assumptions about the geometry of a tidal encounter, in the resolution limits of the instruments that took the data. And that kind of disagreement, that careful, argued, unresolved disagreement between serious people, is actually the most truthful picture of where we stand. If you find that comforting rather than frustrating, if the fact that we're still arguing about whether this object is a galaxy or a tail strikes you as a beautiful kind of honesty, then you're listening to this the right way. Because the universe is not obliged to hand us clean answers. It hands us signals. We do the interpreting. And sometimes the signal is ambiguous, and the right thing to do is say so. So let Virgo HI21 sit in its ambiguity, somewhere in the outer regions of the Virgo cluster, spinning or tumbling or drifting in ways we haven't fully decoded. It's there, in the radio. Quiet, unresolved, one of the more honest questions in modern astrophysics. Now, there is something else I want to tell you about. Something older than Virgo HI21, and older than Dragonfly 44, and older even than the phrase ultra-diffuse galaxy, which would have meant nothing to anyone as recently as 2015. Because the phenomenon of galaxies that are much larger than they appear, objects whose sheer physical size is wildly out of proportion to their starlight, this is not a new discovery. It's a category that has been with us, quietly, since 1986. And the way it was found is one of those stories that reminds you that science sometimes moves not by grand design, but by accident and patience, and a slightly unusual way of looking at old photographs. David Marlin is an astronomer, and also a photographer. Actually, more precisely, he is someone who spent many years developing new techniques for enhancing astronomical images on photographic plates. The glass or plastic sheets coated in light, sensitive emulsion that observatories used to record the sky before digital detectors took over. His specialty was coaxing faint detail out of images that seemed at first glance to show nothing in the regions of interest. A kind of photographic archaeology. Taking an old plate and asking, what's hiding in the low-contrast regions that a quick look would skip right past? In 1986, while working with photographic plates from the United Kingdom Schmidt telescope in Australia, Marlin discovered something that nobody expected to find, a spiral galaxy. A large spiral galaxy, in fact, with a disk extending out to something on the order of 650,000 light-years, several times the diameter of the Milky Way. A truly enormous disk, wider than almost any galaxy known at the time, spanning hundreds of thousands of light-years of space in a slow, flat spiral. But it had been missed. Completely missed. For years and years, it had been sitting there in the data, overlooked by standard surveys, invisible to conventional photographic analysis. Its surface brightness was too low. Its light was spread too thin across too large an area so that any given patch of sky in its direction just looked dim and blank and unremarkable. 1,000 times, probably, an astronomer had glanced at a plate showing that part of the sky and seen nothing worth noting. The galaxy was hiding in plain sight, beneath the threshold of what a quick visual inspection would catch. Mallin's enhanced techniques changed that. By carefully stacking and processing the photographic plates, by bringing up the faint contrast that standard development left in the noise, he revealed the spiral arms and the disk, and the unmistakable structure of a giant galaxy that was simply too quiet, too faint per unit area of sky, to be seen any other way. It was given the name Malin 1, and Malin 1 is in every sense a giant. Its disk, stretched out to those 650,000 light-years, makes the Milky Way's roughly 100,000 light-year disk look modest. It has a visible central region, a bright bulge with a compact bright core, but surrounding that is an extraordinary, gossamer-thin spiral structure reaching far out into space, so diffuse that its outer regions contribute almost nothing to the total light that any single square inch of sky above it carries. Its surface brightness, the central, relatively brighter part aside, falls off quickly to values that put it in the same territory we've been talking about all night, fainter than 24 magnitudes per square arcsecond, approaching the glow of the night sky itself. It's a low-surface brightness galaxy, which is the more technical, broader term that covers objects like Malin 1, the class that would later give rise to the ultra-diffuse label for the most extreme examples. And its discovery in 1986 proved something important that sometimes gets forgotten in the excitement over newer findings. This category. Galaxies that are much physically larger or much more extended than their light lets on, was not invented by Pieter van Dokkum and the Dragonfly Array in 2015. It has been with us for 40 years. Malin 1 was the giant that stood mostly unseen in the library, while newer and stranger relatives were found and named and debated. What Malin 1 showed back in 1986 was that we could be systematically missing a portion of the galaxy population simply because our surveys were calibrated to find things that were bright and compact and well concentrated. If a galaxy spread its stars thinly enough over a large enough area, it fell below the detection threshold of standard optical surveys. It was there. It was real. It had stars and structure and gravity, and presumably a dark matter halo, and everything else a galaxy is supposed to have. But its light was diluted by distance and diffusion to the point where the ordinary tools of optical astronomy passed right over it. You needed either a new technique, as Mallin's photographic enhancement provided, or a different kind of signal altogether, like radio waves at 21 centimeters. And that raises a question worth sitting with. If we could miss Malin 1, which is an enormous spiral galaxy spanning 650,000 light-years, simply because its surface brightness was too low for standard surveys, what else might we be missing? What other population of objects, larger or smaller, more diffuse or more compact, might be sitting in the data right now? Invisible to the tools we've been using, waiting for the right technique or the right instrument to pull them into view? We'll come back to that. Or rather, it will come back to us. But first, the gas clouds. Because Virgo HI 21 and Malin 1 are not alone in the strange category of objects that are mostly or entirely made of things other than visible starlight. There are others, less famous, less dramatically named, but equally important for what they tell us about the space between and around galaxies. Clouds of neutral hydrogen floating without obvious stellar companions, detected in the radio, sitting in the catalogue under designations that sound dry and technical but point to something genuinely puzzling. Gas. A lot of it, gathered somewhere in the cosmos, and hardly any stars to account for it. One of them goes by HI 1225+01. The designation tells you it was found in the High Survey, the 21-centimetre hydrogen survey, at roughly those coordinates in the sky. It's sometimes called the Giovanelli-Haynes cloud, after Riccardo Giovanelli and Martha Haynes, two astronomers at Cornell University who have spent decades mapping the distribution of hydrogen in the universe and have an extraordinary catalogue of discoveries to their names. The Giovanelli-Haynes cloud is a large, extended mass of neutral hydrogen with relatively little associated starlight. Another entry in that recurring, nagging category of clouds that don't quite behave the way we'd expect if all the hydrogen in the universe were neatly organized into star-forming galaxies. What does it mean? Is it a true primordial cloud, a leftover fragment of the hydrogen that didn't make it into a galaxy's star-forming disk? Is it a tidal remnant, gas that was pulled off a larger galaxy by a gravitational interaction and left drifting in intergalactic space? Is it genuinely dark in the sense of having a substantial dark matter halo, or is it simply gas in a region where the density never got high enough to trigger star formation? The honest answer is that cases like HI 1225+01 sit in a genuine interpretive grey zone, the kind of object where the radio data tells you there's hydrogen there, but the follow-up observations needed to pin down its identity and origin and mass are difficult and sometimes contradictory. The category is real, the uncertainty is real, and the uncertainty is useful, because it tells you something about the limits of what the 21-centimetre signal alone can establish. You can hear the hydrogen. You cannot, from the radio emission alone, tell whether that hydrogen is inside a genuine galaxy-scale dark matter halo or simply drifting between larger structures without any significant gravitational container. To answer that, you need velocity information, the rotation curves or velocity dispersions that let you infer the total mass. And you need it at high enough resolution to distinguish a coherent rotating disk from the tangled internal motions of a tidal stream or a turbulent cloud. And then there is the Smith cloud. The Smith cloud is, and there is no other way to say this, a comet made of gas on a galactic scale. It is a high-velocity hydrogen cloud, meaning it is moving relative to the Milky Way's disk at a speed much higher than what the ordinary rotation of the galaxy would predict, and it is on a trajectory that suggests it is falling toward us, falling toward the plane of the Milky Way's disk, on an arc that would bring it crashing in, though crashing here means hundreds of millions of years from now, at speeds that sound fast but play out on timescales that are difficult to imagine. It was first catalogued by Gail Smith in 1963, an astronomer working with radio data who found a large anomalous cloud of hydrogen that didn't fit neatly into the pattern of gas in the Milky Way's disk. Its name has stuck. The Smith cloud is about 9,800 light-years long and about 3,300 light-years across, a substantial object on astronomical scales, though small by comparison to a full galaxy. Its position puts it outside the galactic disk, but not far outside, sweeping in on its long trajectory toward us. And like the Giovanelli-Haynes cloud, and like Virgo HI-21, its hydrogen glows at 21 centimeters, while its associated starlight is essentially absent. No obvious galaxy sits inside it or at its center. It's a mass of gas, moving fast, apparently falling toward the Milky Way, with no clear stellar population to show where it came from. The most careful analyses of the Smith cloud's trajectory and metallicity, its chemical composition, specifically how enriched it is with elements heavier than hydrogen and helium, suggest that it is probably not a primordial cloud of pristine hydrogen left over from the early universe. It appears to contain metals, heavier elements forged in stellar interiors, which means it has passed through or been processed by star-forming environments at some point in its history. One leading interpretation is that it was originally gas that was expelled from the Milky Way itself, blown out by supernovae or stellar winds into the halo, and is now on a return trip inward. In that reading, it's recycled gas, material that was once part of the galaxy, got kicked out and is coming home. A galactic exhalation, returning. But it is, nonetheless, a mass of hydrogen with no current stellar companion, no galaxy sitting inside its hydrogen envelope, shining and identifying itself. In that narrow sense, it belongs to the same recurring category, gas without obvious stars, detected by radio, status genuinely uncertain. What all of these objects, Virgo HI-21, the Giovanelli-Haynes cloud, the Smith cloud, and others like them catalogued over decades of radio surveys, have in common is that they force a question that sounds simple but turns out to be surprisingly hard to answer definitively. What counts as a galaxy? We tend to think of galaxies as things you can see. Wheels of stars, spiral arms, glowing cores, the kind of objects that fill the great photographs from Hubble or the James Webb Space Telescope, grand, lit-up structures that announce themselves across millions of light-years. But what if a galaxy could exist without making itself visible? What if the fundamental unit, the dark matter halo, the gravitational container, the thing that gathers mass and holds it together, could fail to produce significant starlight, or could do so only to a degree so faint that we'd look right past it? What if the lighted things we call galaxies are actually the minority, the bright fraction, the few halos that manage to turn their gas into stars efficiently, while a larger population of halos sits in the dark, their gas present, their mass real, their starlight absent? That is not a rhetorical question. It is an active scientific question with significant stakes for how we understand the universe as a whole. And the answer, as we'll come to, reaches all the way back to the fundamental theory of how structure forms in the cosmos, to the model we call lambda CDM, cold dark matter, and to the embarrassing, still unresolved discrepancy between how many dark halos that model predicts and how many glowing galaxies we actually find. But there is one more thing before we get there. One more thread to follow in the story of objects that are too large or too massive or too strange to be easily explained by the obvious. Go back, for a moment, to what Marlin's discovery of Marlin 1 in 1986 really meant in retrospect. It wasn't just the discovery of one unusual galaxy, it was a proof of concept. It demonstrated that our surveys, even the best, most systematic sky surveys of that era, had a built-in blind spot. Objects below a certain surface brightness threshold were simply not making it into the catalogue. They were being filtered out, not because they weren't there, but because the observational strategy was designed around the expectation that galaxies would be brighter than a certain limit per unit area of sky. Marlin 1 fell below that limit. So did, presumably, other things. How many? Nobody knew. Because if you've designed your survey to miss objects below the threshold, the survey itself can't tell you how many objects you've missed. You'd need a different kind of survey with a different sensitivity to faint, extended emission. That insight that the census of galaxies was probably incomplete in a specific, predictable way planted a seed that grew slowly over the following decades. And it would eventually lead, in a fairly direct line, to the development of specialized instruments like the Dragonfly Telephoto Array, designed from the ground up to catch exactly this kind of faint, extended, low-surface brightness emission that conventional telescopes were not optimized for. Van Dokkum and Abraham didn't build Dragonfly because they expected to find ultra-diffuse galaxies in the Coma Cluster. They built it to study the diffuse light around galaxies more generally. The UDGs were, in a sense, discovered by accident, or rather, discovered by a tool that happened to be the right shape to see things that other tools couldn't. The same thing happened to Marlin. He wasn't specifically looking for giant low-surface brightness galaxies. He was developing photographic enhancement techniques, learning how to pull faint signal out of plates that looked blank at first glance. And one day the technique worked, and Marlin 1 was there. Enormous, old, waiting. There is a pattern here. Not a coincidence, but a lesson that keeps arriving in different forms. The universe does not organize itself according to the sensitivity limits of our instruments. It is simply what it is, full of things at all brightnesses and all scales and all degrees of visibility, and what we find at any given moment is determined not just by what's there, but by what we've built to look for it. Change the instrument, enhance the photographic plate, build the radio dish, array the telephoto lenses, and a hidden population swims into view. What we call the known universe is, to a meaningful degree, a function of what we've had the tools to see so far. That is either humbling or exhilarating, depending on your frame of mind. Tonight, here, lying wherever you are, with the lamp on or off and the world quiet around you, I hope it's mostly exhilarating. The idea that there is more to find, not hypothetically, not philosophically, but literally, concretely more, objects already out there in the data waiting for the right technique, that's not a source of anxiety. It's a reason to stay curious, a reason to come back. The radio sky, in particular, is still being explored in ways that promise more surprises. Instruments like FAST, the 500-meter aperture spherical radio telescope in China, the largest single-dish radio telescope in the world, are mapped to survey hydrogen across vast swaths of the sky with far greater sensitivity than Arecibo could reach in its later years. The Very Large Array, the Westerbork Telescope, the Greenbank Telescope, all of them are participating in surveys of the neutral hydrogen universe that are deeper and wider than anything we had access to when Virgo HI-21 was first announced, or when the Giovanelli-Haynes cloud was catalogued. Each new survey finds new clouds, new anomalous signals, new objects that don't fit cleanly into the existing taxonomy. Some of them will turn out to be tidal debris. Some will turn out to be recycled gas. Some might turn out to be something else, something without a settled name yet. And somewhere in that growing catalogue of anomalous hydrogen, there may be genuine dark galaxies, halos that really did gather their gas, really do have the mass of billions or tens of billions of suns, and really never made a significant stellar population. Not because anything dramatic happened to strip them of their stars, but simply because the conditions for star formation never quite assembled in the right way. Too little density, too much turbulence, gas that never cooled efficiently into the compact, high-density clouds that collapse under gravity and ignite. We don't yet know how many such objects exist, if they exist at all, in a form we'd clearly recognize. Virgo HI 21 is a candidate, ambiguous and contested. There are others in the literature, similarly contested. The category is real as a concept, well motivated by theory, and as yet unambiguously confirmed by observation. That is an honest place to be. It means the question is still genuinely open. It means there is still something to find, and the finding, when it comes, will matter. Not just as a curiosity, not just as another strange thing to add to the collection of strange things, but for what it will tell us about the most basic process in the universe's history. The process by which formless clouds of gas and dark matter became the structured, lit-up, star-filled objects we recognize as galaxies. That process, and the ways in which these dark and ultra-diffuse objects challenge our understanding of it, is where we're going next. Because we've been circling it all this time, mentioning it in passing, the theory called lambda CDM, the cold dark matter model, the simulations that predict far more small dark halos than we see lit-up galaxies. That mismatch, and what Dragonfly 44 and Virgo HI 21 and the whole growing family of ghost galaxies might mean for it, is the payload we've been building toward. But let's not rush there. The night is long, and there's no hurry. Whatever time it is in your corner of the world, wherever your window is open or closed, whatever sounds are coming through or not coming through, let the questions settle for a moment. Let the image of Virgo HI 21 sit, 100 million solar masses of hydrogen spinning in the outer reaches of the Virgo Cluster. Its identity, still genuinely uncertain, 54 million light-years away from the planet where we named it. Let Marlin 1 sit, its gossamer spiral arms stretched out across 650,000 light-years, found by accident on a photographic plate in 1986, because a photographer decided to look more carefully at the faint, overlooked regions of the image. Let the Smith cloud sit, falling toward us across the Milky Way's halo, trailing its long arc of recycled hydrogen through the dark above the galactic plane, patient and enormous and almost impossible to see. These are not the only strange things in the sky, but they are among the strangest that point in the direction we've been walking tonight, toward the question of what a galaxy really is, and what it means for something to exist in the universe without the courtesy of announcing itself in starlight. The universe, it turns out, does not owe us visibility. It makes its structures, and some of them glow, and some of them barely do, and some of them may not glow at all. And we, with our radio dishes, and our enhanced photographic plates, and our arrays of telephoto lenses, keep finding ways to listen and look and coax the hidden things into view, one signal at a time, one surprising, patient discovery at a time. If you're still awake, and it's perfectly fine if you're not, there's more coming. The mirror image of Dragonfly 44, the galaxy that had almost no dark matter, the distance dispute that made one measurement flip to its opposite, the 1,000 ultra-diffuse galaxies in the Coma Cluster alone, and the 2 stories astronomers tell about where they came from, and what any of this means for the deep, old, still contested model of how everything in the universe got its shape. That's where we're headed. Slowly, no rush at all. So, the mirror image. We've spent a good part of tonight walking in one direction, toward the dark, toward galaxies swollen with invisible mass, toward hydrogen clouds spinning in the void, toward Dragonfly 44 with its faint sprinkle of stars and its enormous, lightless halo. The whole story, so far, has been about things that have more than their share of darkness. objects weighted down with invisible matter far beyond what their starlight could ever suggest. But the universe, as it turns out, doesn't tell only one kind of strange story. In 2018, Pieter van Dokkum, the same astronomer who led the team that found Dragonfly 44, the same Dragonfly Telephoto Array, those bolted-together Canon telephoto lenses pointed at the Coma Cluster, found something that pointed in precisely the opposite direction. Something that shouldn't exist, by the same logic that made Dragonfly 44 so unsettling. A galaxy with almost no dark matter at all. Its name, which is not exactly poetic, but is at least precise, is NGC 1052 DF2. And it changed things. Let me set the scene slowly, because it deserves the care. Van Dokkum and his collaborators had been using the Dragonfly Array and other instruments to survey the neighborhood of a large elliptical galaxy called NGC 10 and 52. It's a fairly ordinary giant elliptical, sitting out there roughly 65 million light-years away, the kind of galaxy that anchors a small group of companions. And in that neighborhood, they found something small and faint and diffuse, another ultra-diffuse galaxy, the same general class as the objects we've been discussing all night. Faint, spread thin, easy to miss. But when they looked more carefully, when they measured the motions of the globular clusters orbiting inside NGC 1052 DF2, using those old stellar fossils as tiny speedometers, they found something that stopped them cold. The stars were barely moving, and that matters enormously. Because if you remember what we learned with Dragonfly 44, that the speed at which stars and clusters move inside a galaxy tells you how much total mass is pulling on them, then a galaxy where everything is moving very slowly is telling you something stark. There isn't much mass here. The stars alone, the visible ones, almost entirely account for what's there. There was, in other words, almost no dark matter. Now, take a moment with that. Sit with it. Because the standard story, the one we've been building all night, the one behind Dragonfly 44 and Virgo HI 21, and the entire framework of how galaxies form and what gives them their heft, says that dark matter is the skeleton, the scaffolding, the thing that forms first, collapses first, draws gas in, and lets stars ignite. Every galaxy we'd ever measured, every one, seemed to come with a dark matter halo that outweighed the stars by a factor of 10, or 100, or 1,000. Some, like Dragonfly 44, seemed to be almost nothing but dark matter. The stars were the decoration. The dark matter was the building itself, and here was a galaxy that had apparently been built without the foundation, or had lost it, or had never gathered it in the first place. NGC 1052 DF2 is, by the measurement Van Dokkum's team published in 2018, something like a normal dark matter galaxy missing its dark matter, a house with no walls, an ocean liner with no keel, something that by all rights should not be able to maintain its shape or hold its stellar population together, and yet there it was, sitting quietly in the neighborhood of NGC 1052, minding its own business, with its globular clusters drifting along at modest, unhurried speeds that implied a mass almost entirely accounted for by the stars themselves. And then, in 2019, they found another one, NGC 1052 DF4. Same neighborhood, same host elliptical, same disturbing lack of dark matter by the same line of reasoning, as if the galaxy NGC 1052 had a peculiar talent for spawning companions that had somehow been stripped or starved of the invisible mass that every other galaxy in the universe seemed to carry. Two galaxies, two opposite shocks, both from the same team, both pointing at the same unsettling conclusion. Now, before we go further, because you may be lying there half asleep and wondering, quite reasonably, whether this is getting complicated in a way that feels more like anxiety than wonder, let me say gently that it's not. It's actually one of those places in science where a puzzle that looks like it breaks everything turns out, unexpectedly, to be one of the most compelling pieces of evidence for the thing you'd expect it to break. Let me explain that carefully. The obvious question, when you hear about NGC 1052, DF2 and DF4, is, does this mean dark matter doesn't exist? If a galaxy can get along without it, maybe dark matter is just a mistake in our accounting. Maybe the gravity of ordinary matter behaves differently on large scales than we think, and what we've been calling dark matter is actually just our equations being wrong. This is not a fringe idea. Incidentally, it has a name, Modified Newtonian Dynamics, or MOND, and it has serious proponents, and it has explained some observed galaxy rotation curves reasonably well for decades. It proposes that below a certain threshold of gravitational acceleration, gravity is stronger than Newton's formula predicts, and that extra grip is what astronomers have been misidentifying as dark matter. But here is the thing. Here is the quiet, devastating thing about NGC 1052 DF2. If dark matter doesn't exist, if what we've been calling dark matter is really just modified gravity, a quirk of how gravity behaves at large scales, then every galaxy would show the extra pull. You couldn't have some galaxies with the effect and some without. Modified gravity applies everywhere, the same way ordinary gravity does. A galaxy is a galaxy. The equations don't selectively switch off for some of them, and yet here is a galaxy that genuinely seems to be missing the excess mass. The stars are moving at speeds that can be entirely explained by the stars themselves. There is no extra pull from anywhere. Whatever it is, whether it is dark matter or a modification to our gravity equations, it isn't there. You can't reconcile that with MOND. If the extra pull were built into gravity itself, it would be there regardless. The only framework that can explain both extremes, a galaxy like Dragonfly 44 that is overwhelmingly dark mass dominated, and a galaxy like NGC 1052 DF2 that seems to have almost none, is a framework in which dark matter is a real substance, a thing that exists independently, a thing that can, under the right circumstances, be present in enormous quantities, or present in small quantities, or perhaps almost absent altogether. Something you can have more or less of. Not a property of space, not a modification to equations, an actual ingredient that can vary from place to place. The galaxy with almost no dark matter is, paradoxically, one of our strongest arguments that dark matter is real. Sit with that for a moment. It's one of those places where the universe rewards patience. The anomaly doesn't destroy the model. The anomaly deepens it. Now there is, as there usually is in science at this frontier, a catch, or more precisely, a dispute. And it's the kind of dispute that tells you something important about how science works, not in the clean textbook version where experiments settle questions neatly, but in the real version, where everything hangs on a single number that nobody can quite agree on. The number, in this case, is distance. Van Dokkum's team place NGC 1052 DF2 at roughly 65 million light-years away. That's an enormous distance, obviously, farther than we can truly imagine, but in the context of the nearby universe, it's a moderately local object. And at that distance, the physical size of the galaxy, the brightness of its globular clusters, and the inferred masses all hang together in a way that supports the dark matter deficient interpretation. But a group of astronomers led by Ignacio Trujillo looked at the same object and argued carefully that the distance was wrong. Their analysis placed NGC 1052 DF2 considerably closer, around 42 million light-years, not 65. And here is why that matters so much. If the galaxy is closer than Van Dokkum's team think, then everything derived from the distance is wrong too. It would be physically smaller. Its globular clusters would be fainter, which means they'd be intrinsically less luminous and therefore less massive than assumed. And the whole configuration would actually be consistent with a normal amount of dark matter. The dark matter deficit would evaporate, and you'd be left with an ordinary, unremarkable, ultra-diffuse galaxy at a different address. Same object, same data, one disputed number. Two completely different conclusions. This is not a scandal. This is science. Distance in astronomy is one of the most notoriously difficult things to measure, especially for faint, diffuse objects with no standard candle bright enough to serve as a reliable ruler. And the tools available for measuring distance to something like NGC 1052 DF2 involve assumptions about the brightness of its globular clusters, about the surface brightness profile of the galaxy itself, about how to compare it to similar objects whose distances are better known. Every one of those assumptions can be contested. The uncertainty is real. And the debate between Van Dokkum's team and Trujillo's team is genuine, careful, and ongoing. What it illustrates, and this is worth holding on to as you drift towards sleep, is that a single measurement, even a beautifully done one by careful and serious people, can sit balanced on an assumption you'd barely notice. Move the assumed distance by 20 million light-years. And a discovery that challenged our fundamental cosmology becomes a galaxy that fits neatly into the existing story and wanders back into anonymity. The extraordinary claim rests on an ordinary, uncertain number. Distance is the silent variable in almost every headline from the frontier of astrophysics. Almost every time you hear a number attached to a distant object, its size, its mass, its luminosity, its dark matter content, that number is downstream of a distance estimate that carries its own uncertainties, its own assumptions, its own opportunities to disagree. Good science names those uncertainties. The best popular accounts of it carry them forward honestly, rather than dropping them to make the headline cleaner. So the story of NGC 1052 DF2 is not a galaxy with no dark matter, case closed, implications obvious. The story is an object that at one plausible distance challenges our models in a profound way, and at another plausible distance is entirely ordinary, and the people who study it carefully cannot yet agree on which reading is correct. Both interpretations are alive, both are being tested. And the universe, for now, has not clarified things by making the answer easy. That is where that particular question stands tonight. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier. Energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. Now, let's pull back a little. Let's lift our view from the individual objects, from Dragonfly 44 and Virgo HI 21 and NGC 1052 DF2, and look at the population as a whole. Because one of the strangest things about ultra-diffuse galaxies is not any single object, it's how many of them there are. When Van Dokkum's team published their 2015 Dragonfly survey of the Coma Cluster, they weren't just announcing Dragonfly 44, they were announcing a population. In a single survey, using those arrays of camera lenses pointing at one cluster, they found 47 large ultra-diffuse galaxies. Not one or two, 47. Objects as physically large as the Milky Way, each with a surface brightness so low that every previous survey had simply missed them, the way you might miss a ghost standing in a room because you were looking at the furniture. 47 is already a lot. But then the surveys got bigger. Follow-up work with the Subaru telescope and its hyper-suprime cam, a different instrument, enormous and powerful, built to image large areas of sky with exceptional sensitivity, pushed the count in the Coma Cluster alone into the hundreds. And then over 1,000. Over 1,000 ultra-diffuse galaxy candidates in one cluster. Let that number rest for a moment. 1,000. In one cluster. These are not rare accidents. They are not one-off curiosities to be marvelled at and set aside. They are a population, a common hidden population that was sitting above us all along, too faint to see, too diffuse to trigger the detection thresholds of the surveys that came before the Dragonfly era. The sky we thought we understood, the catalogue of galaxies we thought was reasonably complete for the nearby universe, was missing an entire category of object that turns out to be everywhere. And they don't only live in clusters. Ultra-diffuse galaxies have been found in the Virgo Cluster, in the Fornax Cluster, in smaller groups, and in the isolated field between clusters, which turns out to be important, because the environment a galaxy lives in tells you something about the mechanisms that might have shaped it. This is where the two stories begin. The two competing explanations for what these things are and how they got to be the way they are. The first story goes something like this. Once upon a time, actually, billions of years ago, in the early universe there were small dark matter halos. Halos with enough mass to begin gathering gas, but not as much mass as the halos that would become the Milky Way or Andromeda or any of the grand spirals we see nearby. Small halos, and inside some of those small halos, in certain special circumstances, star formation began. Stars ignited, and the biggest, most massive stars among them burned bright and hot and fast, and when they reached the end of their lives, they exploded. Supernovae, again and again. A cascade of stellar detonations releasing enormous amounts of energy into the surrounding gas. In a small halo, with relatively shallow gravitational wells, all of that supernova energy can do something dramatic. It can blow the gas around. Violently, the repeated outbursts of dying massive stars stir and heat and physically redistribute the gas, and the gas, in a halo that isn't very deep or very tightly bound, can be driven outward. Not lost necessarily, but flung into wider, more diffuse orbits. And as the gas moves out, as the gravitational center of mass shifts and sloshes, the stars follow. They get flung outward too. A galaxy that started compact becomes, through repeated cycles of star formation and supernova feedback, progressively more extended, more diffuse. A dwarf inflated into a giant. A small, dense galaxy puffed up into something that spans tens of thousands of light-years, with the same number of stars it started with, just smeared across a much larger area. This is sometimes called the supernova feedback model, and it's supported by cosmological simulations, elaborate computer models of how structures form and evolve in a universe full of cold dark matter and ordinary gas and the feedback from stars. The simulations of DeCintio and collaborators, among others, show this mechanism producing objects that look, at least in some of their properties, quite like the ultra-diffuse galaxies we observe. Not perfectly. Not every detail works out, but the broad strokes are there. A small galaxy, a burst of vigorous star formation, a wave of supernova feedback, a redistribution of matter, an end product that is large and faint and spread thin. In this story, the ultra-diffuse galaxies are dwarfs in giants' clothing. They are small in mass and small in stellar content, but they've been puffed up by their own violent histories into something that occupies a much bigger volume of space than you'd expect. The second story is different, and it goes like this. In the early universe, there were also larger halos, not the halos of dwarf galaxies, but halos with the mass that would normally lead to something like a Milky Way or bigger. Enough mass to draw in a lot of gas, and in a dense environment, a galaxy cluster, where everything is close together and the cluster itself contains an enormous amount of hot gas and strong gravitational tides, some of those halos suffered a catastrophe before they ever really got started. The cluster tore away their gas, or heated it, or both. As a galaxy-scale halo falls into a cluster, it is subject to a process called ram pressure stripping. The hot intracluster gas, the thin, scorching medium that fills the space between galaxies in a cluster, acts like a wind on the infalling galaxy's gas reservoir. Given enough velocity and enough time, it strips the ordinary gas right out of the halo, leaving behind the dark matter and whatever stars have already formed, but removing the fuel for any further star formation. Stop the star formation early enough, in a halo that would otherwise have become a large galaxy, and you end up with a red, quiet, quenched system. The stars that exist are old and fading, no new ones are coming, and the whole structure is frozen in an early state. If the gas was stripped before the galaxy had time to build up a proper stellar disk, what you'd have left is a large dark matter halo with a small, aging stellar population spread across it. A failed giant. An object that had the mass to become something grand and never managed to. In this story, the ultra-diffuse galaxies in clusters are not small things puffed up. They are large things that failed. Galaxies that were robbed of their raw material before they could use it and are now sitting in the cluster like empty shells, faint and large and quenched. Their dark matter halos intact, but their stellar populations arrested at an early sparse state. These two stories are not the same. They predict different things. A puffed-up dwarf should have a relatively small dark matter halo. It started small, and puffing up doesn't add mass. A failed giant should have a large dark matter halo. It had the halo of something massive, but just didn't convert that mass into stars. And that distinction, in principle, should be testable. Measure the mass of the halo via velocity dispersion, via the abundance of globular clusters, and you should be able to tell whether the halo is small or large. Dragonfly 44, with its huge inferred mass and its rich globular cluster system, looks more like a failed giant than a puffed-up dwarf. Something with a halo in the range of 1 trillion solar masses, even accounting for the revision downward from the 2019 work, did not start as a small thing and get blown outward. It started massive. And it barely made any stars. But other ultra-diffuse galaxies, in other environments, especially the ones found in isolation, away from clusters, where ram pressure stripping couldn't have operated, look more consistent with the puffed-up dwarf picture. The isolated ones don't have a cluster to blame for stripping their gas. If they're going to be explained, supernova feedback is a more natural candidate. And this is the honest and somewhat humbling state of the field. Both mechanisms are probably real. Different ultra-diffuse galaxies probably form through different channels. Some are inflated dwarfs, some are failed giants, Some are tidal debris, shredded remnants of encounters and mergers, like the possible tidal tail reading of Virgo HI 21. That might not qualify as independent galaxies at all by a strict definition, but exist nonetheless, glowing faintly in hydrogen and drifting in the dark. The category we call ultra-diffuse galaxies may be less a single natural class and more a taxonomic convenience, a label we applied to everything that looked faint and spread out and large, without yet knowing whether those things all got that way the same way. That's uncomfortable in a way. We like our categories to be clean. We like a class of objects to have a story that explains all of them. But the universe doesn't organize itself for our convenience, and the best science acknowledges when a label has been stretched over more variety than it can neatly contain. So we live, for now, in a world where ultra-diffuse galaxy means something big and faint that we're still trying to understand. Which brings us, gently, to the largest stakes. The deepest question that all of these objects, taken together, are quietly asking. In the standard picture of cosmology, the model that has survived the most rigorous testing and that the vast majority of astronomers use when they try to explain how the universe got its structure. The universe is filled with two things that aren't ordinary matter: dark energy, which drives the accelerating expansion, and dark matter. Cold dark matter, specifically. Dark matter that was slow-moving in the early universe, clustering gravitationally into halos that then became the seeds for everything: clusters, galaxies, stars, planets, you. This model is called lambda CDM, which is a somewhat cryptic acronym that stands for the cosmological constant plus cold dark matter. But what it describes is a universe in which the large-scale architecture was built by invisible scaffolding before a single star ever turned on. Lambda CDM is an extraordinarily successful theory. It predicts the large-scale structure of the universe, the cosmic web of filaments and voids and clusters, with remarkable precision. It accounts for the patterns we see in the cosmic microwave background, that faint thermal afterglow of the early universe. It explains the way galaxies cluster on large scales. For the universe as a whole, on the grandest scales, it works astonishingly well. But on small scales, there are tensions. Not contradictions, exactly, but places where the predictions and the observations are not perfectly aligned, and astronomers have been quietly arguing about those discrepancies for decades. One of them is called the missing satellites problem, and it goes like this. When you run a simulation of how the universe evolves inside the lambda CDM framework, when you let the computer model the gravitational collapse of dark matter halos from the early universe to the present day, you get a lot of small halos. Many more small halos than you get large ones. This is a natural feature of cold dark matter. Small things form first, then merge and build up into larger structures. And around a galaxy like the Milky Way, the simulations predict that there should be hundreds, maybe thousands, of small dark matter subhalos orbiting in the halo of the larger galaxy. We don't see hundreds or thousands of satellite galaxies around the Milky Way. We see a few dozen. Where are the rest? This is the missing satellites problem, and it has been discussed, debated, and worried over for many years. There are several proposed solutions. Maybe the small halos exist but are empty, starless dark matter halos, invisible because they never managed to light up. Maybe reionization, the period in the early universe when the first stars flooded space with ultraviolet radiation and stripped the gas from small halos before they could form stars, silenced many of them before they ever had a chance. Maybe supernova feedback, the same mechanism we discussed for puffed-up dwarfs, blew the gas out of the small halos and shut off star formation permanently. Any or all of these might be true. And here is where the dark galaxies and the ultra-diffuse galaxies connect to the deepest layer of the story. If there really are hundreds of small dark or nearly dark halos orbiting the Milky Way and other large galaxies, they should sometimes be detectable, not as visible galaxies, but as gravitational influences, or as faint radio signals, or as the occasional objects that Dragonfly and Subaru are beginning to reveal. The ultra-diffuse galaxies in the Coma Cluster, over 1,000 of them now, might be representatives of that predicted but never quite seen population. The dark galaxy candidates like Virgo HI-21, the spinning hydrogen clouds with no stars, might be the extreme end, halos so thoroughly failed at star formation that even the faint stellar residue of an ultra-diffuse galaxy never coalesced. They might be the missing satellites, the ghosts the simulations predicted and observers couldn't find. Or they might not be. The simulations are not perfect. Lambda CDM is not perfect. There's a related tension called too big to fail, which points to a different aspect of the same problem. The simulations predict subhalos that should be too massive to have remained dark, and yet we don't see them lit up. The model is under pressure at these small scales in ways that are real and acknowledged and as yet unresolved. What the dark galaxies and ultra-diffuse galaxies give us is a new observational window into precisely the mass scales and formation histories where the theory is under stress. They are not proof that lambda CDM is wrong. They are, if anything, a new testing ground, a set of objects whose properties, if we can measure them carefully enough, might help us distinguish between variations of the model, or find the places where it needs revision, or confirm that the basic framework is sound and the discrepancies are just the result of messy physics we haven't fully modelled yet. The universe is giving us data. We are slowly learning to read it. And that, perhaps, is the most honest and most satisfying place to land. Not with a neat resolution. Not with "and so astronomers figured it out, and the answer was thus, and everything made sense." But with a picture of a community of people scattered across observatories and universities and simulation clusters, pointing instruments at things that are barely there, arguing carefully with each other about what the faint signals mean, updating their models, revising their numbers, acknowledging when a headline result needs to be walked back, and continuing, patiently and persistently, to ask the old question in new ways. What is out there in the dark? How much of the universe is invisible to us, and in how many different ways? What does it mean for a galaxy to exist? We've been walking through this territory together for most of the night. Starting with Dragonfly 44, hanging in the Coma Cluster 320 million light-years away, the size of our galaxy and 100 times less bright. Learning about the 21-centimeter line, that radio song of neutral hydrogen humming at 1420 megahertz, the same frequency engraved on the Pioneer and Voyager plaques as a marker for intelligent life to recognize. We use it to find galaxies, and we put it on our greeting to the cosmos, and in that small fact there is something quietly lovely. Moving to Virgo HI-21 and the honest open argument it represents, dark galaxy or tidal ghost. We left that question open, because it is open. Following the thread through Marlin 1 and the Smith cloud and the recurring category of gas without stars. The universe's habit of building things that don't announce themselves in starlight. And then the mirror image. DF2 and DF4, the galaxies with almost no dark matter. the strange and counterintuitive logic by which their deficit argues for dark matter's reality. The distance dispute at the heart of it, and what that dispute teaches us about how much of what we know hangs on a single uncertain number. The 1,000 ultra-diffuse galaxies in the Coma Cluster alone, and the two competing stories about where they came from, puffed-up dwarfs and failed giants, supernova feedback and ram pressure stripping, small things inflated and large things arrested, the missing satellites, the theoretical stress points, the open questions that remain open. What I want to leave you with, as you settle into whatever part of the night you've reached, is something that isn't anxiety and isn't false comfort. It's something more like wonder at the actual state of things. We live in a galaxy, the Milky Way, that is itself mostly dark matter. The stars you see on a clear night, the entire visible spectacle of the night sky, represents a small fraction of the mass of the structure we inhabit. The rest is dark, has always been dark. And out there, in the Coma Cluster and the Virgo Cluster and the Fornax Cluster and every other dense collection of galaxies that astronomers have surveyed with new instruments, there are hundreds of billions of solar masses of invisible material organized into objects we only recently learned to notice. Objects that share the same cosmic neighborhood as the grand spirals and giant ellipticals we've been cataloguing for over a century, but that sat unnoticed, too faint, too diffuse, too quiet to trip our previous thresholds. And they've been there the whole time, patient, occupying their volumes of space, cycling their ancient gas through their hydrogen halos, tending their old globular clusters, those dense, wandering balls of 100,000 stars each, which seem to remember something about the galaxy's original mass, even when the stars themselves have thinned to near invisibility. The universe has been keeping these things, and we simply hadn't yet built the right instrument to see them. The Dragonfly Telephoto Array, those bolted-together consumer camera lenses, humble and inexpensive by the standards of modern astronomy, found Dragonfly 44 and 46 others in a single sweep. The Subaru telescope and its hyper-suprime cam found over 1,000 in the Coma Cluster. Arecibo and the Very Large Array and the other radio dishes have been listening to hydrogen clouds that optical telescopes couldn't find for decades. FAST, the enormous Chinese radio telescope completed in 2016, is listening still. The instruments get better, the surveys get deeper, and the universe, each time, turns out to contain more than it showed us before. That is not a crisis. It is not a sign that we don't know anything. It is the normal condition of science at the frontier. Every generation of astronomers has found that the universe is larger, older, stranger, and more varied than the previous generation knew. And every time, the surprise has been generative. It has pushed the models. It has sharpened the questions. It has opened new fields of inquiry that didn't exist before. You, wherever you are tonight, in your bed or on your couch or curled against a window with the dark outside, pressing gently against the glass, you are inside one of those structures. You are made of ordinary matter, which is to say, you are made of the minority constituent of the universe, the stuff that lights up, the stuff that burns and glows and organizes itself into proteins and thoughts and questions. The dark matter passes through you without stopping, right now, just as it always has. And somewhere out there in the Coma Cluster, a galaxy the size of the Milky Way sits with a faint dusting of stars and an enormous invisible halo and no particular interest in whether we have figured it out yet. It was there long before we looked. It will be there long after. Back at the beginning of tonight, I asked you to imagine a galaxy that you couldn't see, a thing as wide as our galaxy, with 100 times fewer stars, detectable only by the faint radio whisper of its hydrogen. And I said that the universe doesn't owe us visibility, that it makes its structures, and some of them glow, and some barely do, and some may not glow at all. I still think that's true, and I think there's something in that truth that, once you sit with it, is not frightening but strangely peaceful. The dark parts of the universe are not absences, they are full, they are structured, they have mass and history, and in many cases their own population of ancient stars scattered like a few remaining embers from a fire that barely caught. They are participating in the gravitational story of the cosmos in every way that a bright gleaming spiral participates. They just declined to advertise. And we found some of them anyway. We listened. We looked more carefully. We built arrays of camera lenses and aimed them at the faint regions between the bright things, and the faint regions turned out to be full. If you're still awake, I hope it was worth it. And if you drifted off somewhere in the middle of the Dragonfly Array, or the distance dispute over DF2, or the long argument about puffed-up dwarfs, that is perfectly fine. The hydrogen is still out there. The dark galaxies aren't going anywhere. Dragonfly 44 is still hanging in the Coma Cluster at 320 million light-years, unhurried and faint and enormous. The questions are still open. They'll be here when you wake up. They've been here for longer than anyone has been awake to ask them. If you've enjoyed this slow walk through the dark, a gentle like or subscribe helps this small channel keep going. Small channels like this one really do rely on your support to keep producing these quiet nights. And if you'd like to tell me where you're listening from and what time it is in your corner of the dark, I'd love to know. Until next time, close the books, dim the lamp. Class is over, sleepy scholar.